So, welcome back to CSE 373. Today on lecture 11, we are going to be talking about a really exciting, kind of a little bit of a departure of kind of the theory land we've talked about so far with algorithmic analysis and kind of our data structures. Today, we're going to really kind of rip apart kind of what's inside your computer, how they work internally, and how that affects the performance of our programs. And so in this lecture, we're going to get a broad sense of kind of what parts are in your computer, how they work, and how they impact the runtime of our programs. And maybe thinking of a data structure, which we're going to call a B plus tree, that's really optimized for how computers work. And we'll talk all more about this later. The first thing I want to talk about is a few announcements. So exercise 2 is due tonight on Friday. You have late days like usual. I don't really recommend using them just because we have exam 1 coming up. But you're definitely allowed to use them if something takes you a little bit longer than you thought. Project 2 is due next Friday, the Friday after. And remember, this project can get a little tricky, especially when you get to that second part of the chained hash map. So maybe this weekend you want to start working on that, at least that first part of the array map, and so you can start getting onto that hash map part. But like before, you also have late days accessible for Project 2. As a reminder, we have this mid-quarter survey out now. It closes on Saturday. This is really helpful for helping us understand how the course is going, what we could do to better support your learning. And specifically, we have a lot of questions about the quiz section on there. So we really appreciate you taking a few minutes to fill that out. We will read every comment in there, and it will really help us out. As a quick reminder, we also have exam 1 coming up. It's going to be released on Monday morning. At 8:30 a.m. and is due 48 hours later at 8:30 a.m. It's a group exam. You can take it in a group of up to 6 people. You don't need a group. You could definitely take it alone. It is not designed to take you all 48 hours. It should only take you a couple hours. But we wanted to give you enough time to provide flexibility in your schedule, also to allow for different time zones. So you could definitely do it alone. We do recommend having a group just because we've heard from students in the past, they felt like they learned a lot talking with their group mates about the problems and coming to a solution together. So if you're still looking for a group, you could definitely use our Discord channel, search for exam groups. There's been people posting there, and it looks like it's been pretty successful in finding people groups so far. We have practice and review materials on the course website, kind of outlining what types of topics you'll see. We'll show you, we have a practice exam from the summer that shows you a very good format of the types of questions we'll ask in this online format. Also, the TAs will be hosting a review session this Sunday. So there will be a review session hosted on Zoom from 6 p.m. to 8 p.m. There's details in a Zoom link on the message board. And again, we highly recommend, even though this exam is open note and you have lots of free time to do it, we do recommend doing some reviewing and some studying beforehand. So just so you have a mental model of kind of looking at what we've talked about so far so that you can be a little bit more effective in group conversations or thinking through problems because you've had that context of kind of looking at what we've seen this whole quarter. Really, for me, the most important part of exam 1 is giving you an opportunity to kind of reflect and look back at what we've seen so far to help form a mental model on kind of how all the topics we've talked about relate to each other. So please go look back at those section problems, the exercises, and our class session handouts. Those are going to be really helpful, and keep those learning objectives in mind that we posted at the beginning of each lecture. So speaking of learning objectives, here are our 3 learning objectives for today. By the way, I should probably mention this, but today's lecture on memory and B plus trees, that is not something we're expecting you to master for exam 1. This is an important concept. We will talk about this and use this kind of framework as we go on throughout the quarter. But this kind of topic of memory and B plus trees, this is not going to be on the exam this Monday. So learning objectives for today. We want you to be able to talk about some terminology we use when talking about computers, namely CPU, RAM, the cache, and disk. So we'll introduce all those terms if you haven't heard of them before. We'll talk about a bit about why arrays tend to lead to better performance than linked list in terms of this thing called spatial locality. And we're going to describe how this B plus tree data structure is designed to minimize disk accesses and be able to look at one of these structures and figure out how you might use a call like get. But we have a non-objective for today, which is to be able to implement this structure, talk about how a lot of the details of how you build it up. We're not really worried about that. We're really talking about the big high-level intuition of what those B plus trees are. So with that, I want to quickly review some of the stuff we talked about earlier this week with binary search trees and AVL trees. So remember, this is tree week. So we started with binary search trees and we're reviewing that. On Wednesday, we talked about this idea of the AVL invariant, which makes sure that all of the nodes are approximately balanced, meaning that the AVL invariant says that each node, its left subtree and right subtree, must differ in height by at most 1. And if your tree is a binary search tree and has this AVL invariant, then it's an AVL tree. And we talked a lot about these AVL rotations to maintain this AVL invariant, and that this AVL invariant really helps us keep the height of our tree short. We said if the AVL invariant holds, then your tree will have height at most theta log n. And we talked that this really is a nice structure. It's actually what's basically used in practice. Java uses a slightly different version of AVL trees, but it's basically the same concept. This is a really good way in practice to make sure that your tree structures always give you this efficient lookup time in that worst case. So the idea behind maintaining this AVL invariant is fixing it and fixing the invariant if it ever got violated. So for example, what we said was each node, we're also going to keep track of the height so that we can easily check if this AVL invariant is violated by its children. So if we ever find one of these, we kind of highlight the 3 nodes that caused the problem. And what I mean by the 3 nodes is you find the lowest most node in the tree that violates the AVL invariant. In this case, it was that node 1, because its left child, the empty tree, has height -1, and its right child, 5, has height 1. That difference is 2, and so we violate the AVL invariant at node 1. And then we highlight the 2 other nodes that we kind of touched on our way down to do this insertion. And then, because we're in this line case, we kind of pick up the node with the 5, lift it up, and then let everything else fall down to gravity. And now 5 becomes the new root of this subtree, where the 1 is to the left and the 8 is to the right. So we talked about this being a left rotation because the thing on the left fell down. And we talked about applying it in this line case where everything's going to the right. We talked about a lot of other cases. There's 4 total cases. 2 of them are these nice and simple line cases where you can just pick up a node and everything drops. But then we also talked about these more complicated kink cases where it kind of you maybe insert it to the right and then the left, or the left and then the right. And we said, well, our rotations don't really know how to handle this, so we need to do a double rotation. Do 1 rotation to get you to a line case, and then you can solve it with what we talked about earlier. So this slide is going to be really helpful in maybe being a bit of a cheat sheet for whenever you're trying to solve an AVL rotation problem. And then also we'll have other slides from that slide deck on Wednesday that shows you the general rule for any arbitrary tree with any arbitrary subtrees, how these rotation rules work. And if you ever get stuck on these, you can always talk to us in office hours or about them because they can be a little tricky sometimes. Now, one last thing I want to highlight just to kind of remind us is the reason that these AVL rotations work is that you only ever need to do 1 of them. And when I say 1 rotation, I really mean one single rotation or a double rotation, but you only have to fix 1 node. Once you've done that, the whole tree is fixed. And to kind of remind you of this intuition, when we talk about invariance, we always talk about you assume it's true before your function call, and then whatever you need to do, whatever you need possible to maintain it after your function call. So suppose we have this tree, and it might have some arbitrary tree above it and to the side. Suppose we have this tree, and it's going to say, because we have this AVL invariant, we're going to assume it's currently an AVL tree. Then when we do an insertion to insert this number 11 down at the bottom, we now have violated the AVL invariant. But remember, it was just adding that new node at the bottom that violated the invariant. Before, everything was fine. Everything in that red triangle was height 2. And because our AVL invariant was held before we did this insertion, it means that the other nodes everywhere else were fine with this tree being height 2 because the AVL invariant held. So when we inserted this new node, we've now violated the invariant. We now have to fix it. And what I argue to you is you only have to change 1 node. You only have to figure out what's the lowest node in the tree that this invariant has now been violated. In this case, it turns out to be the 8 because its left child 7 has height 0 and its right child 10 has height 2 now that we've done this insertion. And so then we do a rotation. I'll let you figure out what type of rotation we do and how. But my argument is once you do a rotation, the height of the subtree goes back to 2. A rotation will always decrease the height because we've always lifted that node up. And we kind of rotate it. In the case of this rotation, we kind of move everything else down. But this operation of the rotate moves the height up 1. So now we no longer have a height of 3. We've restored the height of the subtree back to 2, which we said was totally fine from the perspective of the rest of the tree because our AVL invariant was satisfied before when the height was 2. So this is kind of the intuition as to why we only ever need to change one spot in the tree. You always just find the lowest node that violates the invariant and do a rotation with respect to that node, following our rules of which rotation you want to follow. Okay, so now what are we going to be talking about for the rest of lecture? So in this video, we're going to be talking about what your computer memory looks like and talk about some terms that we'll use to talk about computer memory. In the next video, we'll talk a little bit more about how memory is used in your programs. And then finally, we'll introduce this new kind of very memory-oriented data structure, very practical in the sense of what trying to optimize for certain types of operations that your computer does and avoid very slow ones. So before we can dive into like what's memory, how it's used, we should kind of make sure we define our terminology of like what is a computer. At the simplest level, you should think of a computer as being 2 components. It's a CPU, a central processing unit, which is like the brain of the computer. Whenever you're running operations like listening to Spotify or running a Java program, the CPU is like spinning around really, really, really fast and doing some computations at a blazingly fast speed. So it just does, it's really good at very simple tasks like math and doing some computations. So CPU is like the brain. And then you also have in your computer RAM or memory. RAM stands for random access memory. And you should think about RAM as being like your notebook that you write things down in. This is where you store your data, your partial computations that you're saving for later. And this isn't necessarily a part of the computer, but because it's October, things are kind of spooky. You can imagine like a skeleton arm reaching out of your brain to write down in the notebook. But there is a way for your brain to talk to the notebook and write values down and read values there. But when you talk about your computer having 16 gigabytes of RAM, it means your notebook can store 16 gigabytes of stuff. You can write down as much stuff as you want as long as it fits in that memory limit. So RAM stands for random access memory. And RAM is kind of where all of your programs running on your computer store their data. So things like their data structures, like a list or a map or whatever, the variables, the method call frames from recursion, everything is stored in the memory of your computer. So if you ever open up like on Mac, it's called Activity Monitor. I forget what it's called in Windows. I think it's like Task Manager or something like that. You can get a list of all of the programs running at your computer at once, and you can see how much memory they're taking up. You can also look up how much CPU they're using, how much CPU time they're using. This RAM, which we sometimes just call memory or main memory, is kind of the place where everyone is storing their data. So for example, you can see IntelliJ is using just shy of 1 gigabyte of memory, storing all of the things necessary to help you develop your code. Google Chrome tends to be a pretty big memory hog because it needs to keep track of a lot of information about what tabs you're using and everything like that. Zoom might keep track of like who's in the call right now, so I might have a data structure for who's in the call. Kind of maybe some video buffers for keeping track of what frame is currently displayed on the computer. Any data that needs to be stored, for the most part, will be stored in RAM. Now, we'll talk about some other places that data might be stored, primarily this other thing called disk, your hard drive or your solid state drive. We'll get there in a bit. Don't worry about that quite yet. But RAM is kind of like the de facto place. You have like 16 gigabytes or however much your computer has that can store all of this stuff. Now, while RAM is actually like a chip that's on your computer, it's on inside your computer. If you have a part, you can find it. Programmers, for the most part, generally don't think about that. So one of the most important ideas in being a computer scientist is thinking about things at various levels of abstraction. So jumping between abstraction layers to think about something versus as the very low level nitty gritty details versus the very high level useful representation of something. So while the RAM is really a physical chip that is made up of a bunch of circuits, and I have no idea how it works, you usually think about RAM from maybe some programmers would think from the perspective of it being a really big array. So we have this abstraction here where we think about our RAM available on our computer as a gigantic array, 16 gigabytes big, or however much RAM you have on your computer. And this is where all of the variables and linked lists and everything you're making is stored. We usually think about this, we think about this big array as storing all of our data, and we think about it as being indexed like an array. Each spot in memory has a unique address, like the index of an array. And we can use that address to describe which piece of data we're talking about. And actually, we call this RAM random access memory because it does a really good job at providing relatively fast access to any particular index you want. You want to go to index 375, it can get you there relatively quickly. We'll qualify that a little bit more later. So thinking about this big array is going to be really helpful when we think about how our programs are actually kind of run on the computer. So for example, if you're running a Java program and you say something like int a equals 5 and char letter equals z, both of these variables get stored in this gigantic RAM array. Now I'm not going to try to draw 16 gigabytes worth of space on here, so I draw a short version of this. Each variable is going to have its own space. And the value inside that space is the value of the variable. So I'm storing 5 at index 107 in RAM. I'm storing the character z at index 113. In reality, what's really being stored here, RAM just stores everything in binary, bunch of ones and zeros. So all that's actually getting stored here is the binary representation of 5 or z, but we're not going to really talk about that level of low-level details. Now, importantly, usually as a Java program, or for programmers in most languages, you don't really think about where these variables are actually stored physically on your computer. Like, you don't really ever care that the variable a is stored at index 107. And Java does not provide a good way for you to find out that it is in fact stored at 107. They don't want you to really be thinking about exactly where it's stored. So what they usually do is Java, behind the scenes, does a bunch of bookkeeping for you. They keep track of, okay, when the programmer says variable a, what they really mean is the memory that's stored at address 107. And whenever they say the variable letter, what they really mean is referring to the address 113. So Java, behind the scenes, is keeping track of which variable is stored where. Guess what? It's probably also doing that somewhere in memory. It's keeping track of kind of a table of where the variables are stored. When we'll never really think about how do you get to index 107 in RAM, Java does not provide a way to do that. There are other programming languages, much lower level programming languages, like this one really popular one called C. It's kind of old. It has a really big user base. This language C provides a way for you to essentially access any part of your memory, which is cool, but also can let you shoot yourself in the foot if you access the wrong part of memory and things break in really weird ways. So Java eliminates all those details, and it's actually really, really nice that they do so. So this is supposed to be like the simple picture of memory, like you have some variables, but what I want us to talk about is a slightly more advanced application of this, where we think about how does this interact with something like a data structure? What does a data structure like an array or a linked list look in memory? So let's think about data structures and how they're stored in RAM. So for example, whenever you make a new array, we think of arrays as being contiguous blocks of memory. When I say contiguous, what I mean is that all of the blocks of memory are right next to each other. So when you say make a new int array of size 3, it's going to grab a chunk of memory big enough for 3 integers to sit right next to each other. So really the whole array is just one big chunk of memory big enough to hold 3 things of the type that you stored inside of it. And this is actually why array accesses are so fast. When you say, hey, go to index 0 of this array, you're just saying go to 0 away from the start of this array index, 102 in RAM. When you want to go to index 2, you go to 2 spots away from that. Because the computer provides random access really, really well, Arrays provide random access really, really well. And so there's kind of this, just like with our simple variables, ints and characters, Java just stores, okay, when you're talking about this array, you're really talking about the block of memory starting at 102. So we have this nice contiguous block of memory. We can really easily access any part of it. Now, you might wonder, okay, is the story the same for something like a linked list? So remember, with linked lists, we had this really nice picture where you had one node, and it had a reference to the next node, it had a reference to the next node, and it was very nice. You could follow it along, it looked like a little train. Turns out that on your computer, this is going to end up looking a little nastier. So what ends up happening when you make a linked list is there's no guarantee that the memory it allocates for each node is going to be contiguous, or going to even be next to each other at all, or even in order. So you might imagine when you make the first node storing the number 3, that might give you index 114 in memory, but then when you make a new node, it might give you index 108. And so you might be wondering, well, how do I get from one node to the other? That was the whole purpose of having a next field. We had to store, told Java, hey, you need to store another field in this node object that is a reference to the next node. Well, the way that Java actually represents that value in memory is it's actually storing the address of that object in memory. So when you have a reference to the node with the data 7, you're really storing right here in your array the address of that node in memory, address 108 it looks like. And then this node has a block of memory that stores those two fields. It has a data 7. And then its next field stores value 117. And the way we interpret that is, oh, that's the address of the next node. And then maybe we store some value like 0 to represent null for the address. And so, as I mentioned, nodes here do not need to be contiguous or even in order. They can be spread out all over memory. And that's going to have actually a really important implication for what we're going to talk about in our next video about how this memory model impacts our programs. But kind of my super key takeaways here from this video is every piece of data that you're going to be using on your programs gets stored in memory. They have some location that you don't necessarily get to access, but it's behind the scenes, it's there. Arrays are contiguous blocks of memory where all the values in the array are stored next to each other. And linked list might not be. Linked lists might be stored kind of separately all over the place, but references allow you to refer to a particular spot in memory. So a reference or a pointer or whatever you call it is really just the address of some object in memory. So you can know exactly where to go in memory to find that next object. Okay, so that's all I wanted to talk about in terms of RAM, this high-level picture of memory. We're going to talk about in the next video how this impacts the runtimes of our programs.